Hello everyone and welcome to the Matrix in Blender. And with that I don't mean the Matrix, I mean the math kind of Matrix, which may be less fun, but still necessary in Blender 4.2, because we got a whole bunch of new Matrix nodes. Alright, now part of you probably have never really heard about matrices and how to use them. I'm not a professional math guy myself. But I read into it. I think I know the basics. I think I know how to read them. A little bit of the basics behind them as well. I feel like it's easier to understand what they do and how to use them if you have a bit of an understanding of how they work. So we're going to get into that. So these are a few of the new nodes, right? That includes matrices. And by default, you'll see that we now have a bright pinkish output. Or input that is a matrix, right? So we used to have translation, rotation, scale, they are still there, but now we also have a transform that is pink, and that means a matrix, right? Now if I hover my mouse over one of the matrices, we can see what a default matrix is. All right, so this is what you can see right now. On the screen is the pretty much neutral matrix, right? Which means that the input will be the same as the output. And what I mean by that is by default, you can do a matrix transformations. And that basically means that we have, for example, a vector right here of x, y, z. And we can do any type of transformations to this to create a new output, right? A new set of x, y, z. And the type of transformations depends, I am messing up this drawing. The type of transformation depends on what you're looking for, right? So in our 3D viewport, in our item tab, we can see what kind of transformations we have. We've got translation, right? Moving things in a specific axis. And we have got rotation, you know what that is. And we have scaling. Right, and these three things can be combined into a matrix, and we can see that right here as well. The main one, I think of it as the main one, is the combined transform node, right? That combines a translation, rotation, and a scale into a one matrix, right? And that is what Blender uses for pretty much all the transformations, right? It's pretty much the language of Blender, doing any kind of translation, transformation in your viewport, whatever, and there's all a matrix involved, because that is actually used to translate, rotate, scale, transform. So what does that mean? What does a matrix do? Why is it 4x4? If I hover my mouse over, why does it look like that? Well, let me explain that in short terms, right? So at this point where we go from vector 1, v1, to vector 2, v2, there is a transformation that happens, and this transformation is done with a matrix, M, I'm gonna call it. And such a matrix looks like a 4x4 row and column table, pretty much, right? And you can see that when you hover over it, it's between brackets here, but that is basically a matrix, right? And if we draw that in terms that would usually be used, we've got like this, and then we've got 4x4 here. So we could see right now that we have 1, 1, 1, 1 diagonally, and I will tell you why exactly in a second. And the rest was 0, right? 0, 0. Then we've had 0 and 0 and 0 and 0, 0, 0, 0. Right, so that corresponds perfectly with this. So that is the matrix. So that is the default matrix. If we do this transformation to a random vector, whatever vector, we're going to end up with exactly the same vector. And how would you use this as transformation? How would you do this on paper, for example? Is that we have 4 rows, 4 columns. This is basically our x, y, and z axis, right? So basically our vector that you turn around pretty much. And to get from one vector to the other, we're basically going to go through each column, right? So this is going to be the x, the y, and the z column, okay? And then we will have some additions, okay? Which basically means that if we want to go from our default value x, we would now have, for example, our 1 here, and we will do x times 1 is 1x, plus y times 0 is 0, plus z times 0 is 0, plus the last column is, well, unknown yet, because I've not explained that yet, but it's 0 as well in the neutral matrix, right? Which means that we only have 1x, which is basically the same output as the inputs, because we have 1 times the x value. For the second row, we would go for the same thing, right? So x times 0, 0, y times 1 is 1y, z times 0 is 0, and 0 times 0 pretty much is 0. So we would end up with y, the same for the z value. So we would end up with 1x, 1y, and 1z, which means that this is a neutral matrix, all right? And we end up at the same input, same output as the input, okay? Now this fourth column is there to allow for all the transformations that we have. And we don't need like a fourth dimension or anything. All we need to add in our matrix is a 1. And the reason why is because if we have a 4x4 matrix, which is just needed to have all the transformations, and I'll explain that in a little bit as well, we need 4x4. And the only way to do a matrix transformation to a vector is if that vector also has 4 values, right? So we add a neutral fourth value of 1, right? Basically of 1, and that will allow, and I'll explain it right now, translations, all right? Excuse me. If we have the default matrix, we have got a diagonal line that we just used as well to get 1x, 1y, and 1z. And this basically is the scaling of the matrix, right? So we can scale an input vector by changing these values in the matrix, right? If I set these values to be 2, 2, and 2, then we're going to end up with 2x, 2y, and 2z, which means 2 times x, 2 times y, 2 times z. Our whole cube will be scaled uniformly, which will look like this, right? So if I scale this by 2, the transformation matrix behind it looks like this. All right, makes sense. And now that is scaling. All right, so scaling, as you can see, we only need 3 by 3, right? So why is the 4th column and row there? Easily enough, that is there for translations. All right. So as you can see right now, we are multiplying x with the first column, for example, x times 2 plus y times 0 plus z times 0, which means that if we would want to translate this without also affecting, for example, the other values or the scale or whatever, if we want to do an independent translation, which means moving things into a specific axis, we will need to add a value that is independent of pretty much the x, y, or z value. All right, which means that we need to add a 4th column that is independent, which is why we add that number 1. All right, so 1 is going to be there, and that means that we do 1 times a value, 1 times a value here, and 1 times a value here, which is basically just that value that will be added or subtracted from the rest of the row, right? For example, if we will set this value to be 2 as well, we will get 2 times x plus 0 times y plus 0 times z is 2x, and then we would plus 1 times 2 is plus 2, which means that our x output will now become 2x plus 2. Okay, makes sense, I hope. And that is why the 4th column is there as well, and also why that 4th row is there pretty much. Okay, beautiful. I've got a 0 there, I think. So that is what the matrix does, and that also means that these 3 values, right, at the x, y, and z axis that are independent and take care of translation, these are now the translation matrix values, right? So this is where translation comes into play. The diagonal is where scaling comes into play, and rotation is a little bit of a different story, Rotation takes place in 3 columns and 3 rows as well, like a scaling, but it looks a little bit different because a value there would be linked to sine and cosine. Okay, and that is basically what takes care of rotation values and setting these up properly. As like a normal multiplication value instead of having degrees. So we would enter, for example, sine of 90, which I think is 0. If you rotate this in 90 degrees, then that value would also be 0, right? Sine 0. So how that looks in the matrix, right, is as follows. We have a matrix, and let's say we have 1, 1, right? The neutral matrix to start off with. Then let's say we rotate, let me add these values back, x, y, z, 1, and just x, y, z, I guess. Let's say we rotate around the x-axis, and let's see that right here. If we rotate around x, you can see that we move each point. For example, this point is now here, and if I rotate it around x a bit more, the point is now here. Which means that if I draw my axis, z-axis, and my y is going into that direction, right? Y, and this is z. You can now see that our points moved in both the y and the z direction, but not in the x direction, not in this direction, because we are only rotating around that. So the position in the x-axis did not change at all. So that means that once we rotate around an x-axis, we only move a point in the y and z axis. Okay, and the same goes for rotating around y. We only rotate in x and z, and if we rotate around z, we rotate we move in x and y. Okay, so that looks in a matrix as follows. Let's say we rotate around x, then anything with an x linked to it is basically going to be 0, except for, of course, the scaling values, right? Those are going to be 1 or whatever you want to scale with, but not 0 by default. So let's say we scale with x. We can simplify this by making this x, 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 but then x, 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 y, and x, z, right? Because we're basically multiplying x and x here, and x and y there, and x and z there. Same for I, y, 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 x, y, 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 z. And this is gonna be zx, zy, and zz. Alright, the rest I'm gonna leave blank because they don't really do anything for rotations. So let's say we rotate around x, okay? So x is not moving at all, so we're just gonna make that 0 in our heads, which means that we only remain that uniform axis, right? So this will remain as 1, because that is gonna be our scaling value. Then we end up here with an xy that is not gonna be moving, because we are going to rotate around that x-axis. Okay, so we have that x here, and that's gonna just be 0. Then we have an x here as well, that's gonna be 0. And then we have x in the y-axis here as well, so that's gonna be 0. This one has an x, that's gonna be 0. And these 4 all have their own value. So rotating around x will tweak these 4 values in their own way with a sine or cosine function. Right, so that is the rotating for x. Rotate x is going to change these values in the matrix. Beautiful. Then for ry, we can do the same thing. Ry, we think about what changes and what doesn't change. If you rotate around y-axis, and we can then set up the same thing, right? Except for that we now just not include anything with the y, which are the middle axis, right? This cross is going to be everything that is included with y, which means that we're going to have, this is going to be changing with the rotation. And then we have this corner that is going to be changing, so that is xz. We have zx and zz, right? So these corners are going to be changing based on a y rotation, right? And you can fill that in according to that function of sine or cosine, right? You can look it up on Google. It will be exactly the same, but with the actual functions on these places that you can use according to the angle you want to rotate in. Same for rotation around the z-axis, right? We got another matrix, but then the opposite of x pretty much, right? So the z values is everything pretty much in this area, all right? So that's z row there and there. That's all gonna be included, or that's not gonna be moving at all, which basically makes us end up with x, 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 y, y, x, and y, y, right? So these 4 values that are going to take care of that rotation. Okay, once again, get those values from Google or wherever, where you can actually fill in the degrees, calculate those values according to how much you want to rotate. But this is basically what's happening behind the scenes. So that means that the only reason we have that 4th column and 4th row is because the translation is stubborn and can't be done in the 3x3 matrix. That's why we use the 4x4. So how does this really work in the Blender geometry nodes? Well, it's really easy. I just showed you how translation, how scaling, and how rotation is done in this matrix. And you can combine all of these values separately, or you can just combine them by having a preset of translation, rotation, and scale values, right? Combine them in the same matrix. But in geometry nodes, we can just combine them with the node, right? Which is basically going to turn everything into one beautiful matrix, right? And we can fill that in ourselves, or we can get these values from something else, right? Rotation as well, scale as well. We can get the output from somewhere else and input it here, for example, combine it to a matrix, and we can use that later. And now the same thing goes for the separate transform, right? So we can also use, for example, an object info, where we could already split location, rotation, and scale, but now also has a transform output that we can basically separate as well, right? So perhaps these 3 values will be gone at some point, because this node basically takes care of these values. But that is basically what it does, right? So every matrix, every print output has the information of translation, rotation, and scale. And you can separate that at any given point. Now the same goes for a combine and a separate matrix, all right? So that is not really the transformation that you're gonna be separating or combining, but the actual matrix, all right? So we can open up column 1, column 2, column 3, column 4, and you can see that this corresponds with all the values we've been filling in before. Column 1, right? Column 1, X here, row 1, X, Y, Z, for example, right? What we just showed you. You can just separate or create these values on your own, which means that if you, for example, just want to scale this, you can, for example, set row 1, column 1 to 2, row 2 of column 2 to 2, row 3, column 3 to 3, and you can leave this as 1, right? That basically ends up with this. Beautiful. Now you can already see that we've got a 1 pre-filled here. So if I move this to the bottom, for example, near the multiply matrices, you can see that here we have the 1s pre-filled as well, which makes sure that the input and output will stay the same as like a default value. The same thing goes for the combined matrix. For the separate matrix, of course, we are going to be extracting values, which means we won't be able to add values ourselves, combine them ourselves. And we're basically just extracting the values from each of these columns, right? So for example, if you have a transformation and you just want to know how it scales in, for example, the x-axis, right? You can extract that row 1, column 1 value, and you'll have that x scaling, okay? So you can extract all of these values exactly the way you want them to be, okay? Beautiful. What else do we have? Let's see. We've got the combine. We've already went over that. We've got the multiply matrices. That's basically just multiplying transformations. And we've got an invert matrix and a transpose. Wow, what does that mean? Well, an invert matrix is what it says, right? If we have a matrix, we do a specific transformation, and we afterwards do the transformation in inverted way, right? An invert matrix transformation. We will get back to the OG level pretty much, all right? So that is beautiful. And we've got a transpose matrix, which is going to change things a little bit, right? And the way it's going to change is we have, for example, got a matrix here with our diagonal axis, right? Like that. Then what the transpose is going to do is going to flip all of these values across that diagonal direction. Alright, and stuff like the invert and the transpose and an inversion combined can actually take care of, for example, fixing normals if you skew your object, right? If you scale it non-uniformly, your normals may get messed up a little bit, and an invert matrix in combination with a transpose matrix can, for example, fix these normals a bit more. And they can also be used, for example, for swapping out coordinate systems, right? For example, from local to global or vice versa. I think you can even use it to go from like a viewport axis to like whatever. I think there's multiple things you can really do with it. But that is what you basically can use these for. Alright, so you can invert and transpose entire matrices instead of having to individually do location or rotation scale, for example, which can be very useful. Now, something else is the accumulate fields, right? So I just want to mention that this now has a transform input, right? Instead of only having a float and an integer, for example. And now the accumulate fields you can use, for example, for having stacked cubes, right? If you stack cubes on each other, but you give each of these cubes a random scale, then they will intersect, right? But with an accumulate field, you can store pretty much the scale per instance, right? Per object, and it's able to actually stack these cubes on top of each other, because each of these cubes will have its own index, pretty much, right? Its own value, and it's able to stack them according to what value is stored for what instance, pretty much, right? But now you can do the same for a matrix input, right? So before we could, for example, do a random value as an input, which is a float or integer. Now we can actually store entire matrices in the accumulate field and have that apply to different instances as well, right? Beautiful. So one of the things that I'm going to use this the most for, and I'm guessing a lot of you guys are, is for a project point. All right, and that is a fun thing to use because you can just move points according to a transformation matrix, right? So for example, we have a matrix here. We set up a matrix of random values. Let's say we want to apply that to our input. Let me set everything to 0 and the scale to 1. So let's set this as a transform geometry value. I'm going to connect this. Let's set this to be matrix first, right? We have our default components, but we can also set this to be matrix, which allows us to do all of these things at the same time. All right, quite beautiful. Now that is handy, right? It's quite handy. But what I find specifically annoying is that I cannot store, for example, a scale or whatever and plug it into my transform geometry. The same for a matrix. If I want to store this, store named attribute, yes, we now also have the option to store a 4x4 matrix, which is what we've been talking about all this time. Let's name this matrix and actually store that here. If I now just want to use this later on, right, all the way to the back of the node system, if I want to use it then, we will have a named attribute set to a matrix, call that matrix and connect that up. We have an invalid link, okay, because, well, the transform geometry just simply not want to take care of and fields, right, field inputs. So how do we fix that? Well, usually you do it with like a set position, but it's difficult because we need to somehow set rotations up and scale up to be a new position of our points, of our vertices, right? And if you don't want to take care of that, we can now use a project point, right? Which is very handy. So let's just disconnect this. Let's set our attribute matrix to be a transform. We can now connect this and let's connect this here just so we can see what rotation looked like before. We can now connect this to Shift A set position, right? Set that in here. Let's mute our transform geometry for a sec. We can now connect this into our offset. Now by default, that is only gonna do the translations pretty much. Reason why is because we have a starting vector of 0, scaling a vector of 0 is gonna be 0, and basically rotating a vector of 0 is also gonna be 0, right? It's going to be all 0, so we only are going to end up with that translation. Okay, so if you want to actually take care of this the proper way, the entire matrix, we need an input, and we need to give it an input of a position, right? The actual positions of these points before the transformation, so it now knows how to scale and rotate each point according to the origin of the cube. So let's just connect that position node. There we go. And here we are. Now we have it set up to be the offset, right? Which means that it's going to set these points as like an offset from their official location, right? The OG position of the corners, for example, in this case. We can also set this to be our position, right? So there we go. So now we can actually start comparing this. So let's set up that switch node so we can actually switch between the two values. So I want to switch between this and between this, and I actually don't want the transform geometry to connect it here, but the matrix output, the named attribute output. So this transformation is not included there, right? So now we actually have two separate transformations that we can compare. So let's unmute this, connect this up, and see the differences. So right now we're going to end up with the same values, as you can see, right? Beautiful. So let's see. We're gonna scale, transform this, see just if this works properly, rotate this a little bit more randomly, scale it up a bit weird. There we go. If we now switch this up, you can see it is exactly the same, right? So we can now really just easily store a transformation, whether that's gonna be from our inputs here, or whether it's gonna be from an actual transform node, or whether it's gonna be from something else that we stored separately at another given point. We can now combine that, store an entire matrix, which is going to save us a lot of time, and we can just reuse that matrix anytime to rotate, scale, and translate points or an entire mesh in very easy ways, right? So this is a nice workaround to store matrices and use them later on in a transform geometry. So no need anymore to recalculate anything. Or to use, for example, a set position for the translation, a scale elements for scaling, and like a rotate, I don't know, a rotate instance for like rotating. And we can now do it all with just this, right? And it could have been done before, but a little bit harder, I believe. So that's a nice way that I'm going to be using matrices for sure. Obviously there's gonna be some other things you can do with matrices. You can do some fun rotations. I think Cartesian Caramel has a 2-hour long video on how he uses them and how he replaced old nodes with the matrix nodes. So if you are actually interested in that, please have a look at his videos. So that's gonna be pretty much the end. So I hope you now at least have a little bit of an understanding of what the math is behind matrices, why there's a 4x4 matrix, why all of a sudden we're using that to transform stuff instead of doing it the old way, right? So this is Blender's native tongue, so we can now communicate with Blender in a proper way, and that's gonna be a little bit trickier for us to understand and set up, but I believe there will be much more videos actually explaining what each individual node does. How you can use this, for example, to really transform between different orientation systems, stuff like that, and way more intricate work. I hope this gave you a little bit of the foundation, though, the basics. If you enjoyed it, if you learned something, please leave a like, a comment, subscribe. I would enjoy any one of these, and have fun with the matrix, right? Cheers.